In this video, I'm going to take you through Lanthanides, exam preparation. And I've made things easier with, a lot of shortcuts to recall them. So first of all, I'll take you through lanthanide contraction. So number one, lanthanide contraction, and then followed by why europium 2 plus, and cerium 4 plus are stable lanthanide ions. Then the ground state and magnetic moment calculation of lanthanide element, which I'll tell you what to do. And then colors of lanthanides with easy shortcuts, colors of the lanthanide series with easy shortcuts, and then production of elemental metals, and the structure of the lanthanides, structure of lanthanides. So let's get right into it. Let's start. Lanthanide contraction. This is the gradual decrease in atomic and ionic radii of lanthanide element as the atomic number increases across the series. This occurs because the added electrons are filling the 4f orbital, right? The 4f orbitals, which are less effective at shielding the outer electrons from the increasing nuclear charge. So that is typically, generally the definition of lanthanide contraction. Now, let me explain what this exactly means. So generally, this is the structure of an atom, right? So we know that this is the nucleus where it is positively charged, and these are the orbitals, right, with electrons. So the nucleus is positive, and it contains protons and neutrons. So it pulls the electrons, the outermost electrons, towards itself. So the effective nuclear charge, the nucleus has a certain force that pulls the electrons from the cells towards the center of the atom. So let's say this is a nucleus with one shell, and this is let's say a nucleus of two shells containing electrons. So as the number of shells increases, we can get to a point where the electrons in the shells will be repelling each other, right? And this nucleus is also trying its best to pull all these electrons towards the center of the atom. So these electrons, as the number of shells increases, the electrons end up repelling each other, right? Which is called the shielding effect. So the electrons in the outermost shell tend to repel each other, getting away from the effective nuclear charge from the center, right? From the center of the atom. So this effective nuclear charge has a greater effect on the atomic and ionic radii. So for the lanthanide, the 4f orbital, the added electrons are being added into the 4f orbital. So because we are not getting more shells coming together apart from the 4f orbital, so and we know that as the number of electron increases or the atomic number increases, the number of proton increases from the nucleus, therefore increasing the effective nuclear charge. So the effective nuclear charge therefore gets higher and therefore pulls the outermost electron towards itself strongly. So this is why from lanthanide to Lu, the atomic radii or ionic radii decreases, because as we go from left to right, the added electrons are being added onto the 4f orbital, and at the same time effective nuclear charge increasing, pulling the electrons strongly towards the center, causing a decrease in atomic and ionic radii. Why cerium 4 and europium 2 are stable lanthanide ions? Problems like this, you don't have to memorize them, like you don't have to force yourself recording them. Just make reference to your periodic table. Let's look at the electronic configuration of cerium. 4f1, 5d, and then 6s2. And the europium, xenon, 4f7, 6s2. Now we are looking at why cerium 4 and europium 2 are stable lanthanide ions. So looking at the electronic configuration for cerium 4, right? It means let's take cerium in the +4 state, right? So we have two electrons here, 2, 1 electron here, 3 and 4. So at the end of the day, we are going to have cerium to be 4f0, right? That is at the +4 state. And out of europium, we are looking at europium 2, which means europium is going to go away with this electron, right? 6s2 electron. So at the end of the day, we are going to get europium to be 4f7. So what can you say about this? You will see that for cerium, we have the f orbital to be 0. 0 electron in the f orbital, 4f orbital. And for europium, we have 7 electrons in the 4f orbital. And we know that this f orbital has a total of 7 suborbitals, right? So which means that each of the 7 suborbitals are filled singly with electrons. So this gives it an extra stability, right? And here too, we have all the 4f orbital with no electron. So this also increases its stability. So the reason why cerium 4 and europium 2 are stable lanthanide ions are due to their electronic configuration, specifically associated with the half-filled and empty-filled 4 orbitals. So that would be your explanation. The half-filled of europium 2 plus, and then the empty fold of, the 4 orbitals of cerium. This gives them extra stability as compared to the others. So another thing you need to know is, which is very important, is the ground state term and the magnetic moment of lanthanide. The ground state term, let me change this marker. Ground state term and the magnetic moment calculation for the lanthanide series. This is very important because you will be meeting a lot of problems like this, mostly as far as lanthanides are in concern. If you are having an exam concerning lanthanides and actinide series, so there's a need for you to know how to calculate the ground state term and magnetic moment of lanthanide series. And I have a video on this. Actually, I don't want to make this video all that long, so I have a short video which is 30 minutes, 38 seconds, and also a 37-minute 52 seconds video which contain a lot of work examples, and which will help you. So I think you should check that out. Colors of the lanthanides. You need to know the colors of the lanthanides if you are studying lanthanides and actinide series. So I'm going to give you a quick procedure how to record the colors of each element on the lanthanide series. Simple, easy trick. So first of all, I'm going to need you to memorize this in order, right? CGL, yellow, pink, yellow, pale pink. You can say that after me. CGL, yellow, pink, yellow, and pale pink. So now, this C right here stands for colorless, right? Colorless. And the G right here stands for green, color green, right? And then L here is lilac, lilac. So memorize these colors in order. So first CGL, C for colorless, G for green, L for lilac. Then yellow, pink, yellow, and pale pink. Yellow, pink, yellow, and pale pink. Now let's get right to the problem. So we are going to apply the following, this procedure on the elements. So now follow up. We know that for the color chart that we memorize, the first is C, followed by G, and followed by L, right? So C stands for colorless. We are going to look at those elements that are colorless. So what you do, remember, the first two elements, and in the middle, which is gadolinium, and the last two elements are colorless. So first two elements, last two elements, and the one in the middle, which is gadolinium, are colorless. So we are done with our color chart, with color number 1, C. Then we now go to G, which is green. So what we'll be doing now is that we pick one from the left, one from the right, one from the left, one from the right, up to a point that we get to the middle element. So now the second one, you pick one from the left and one from the right. These are green, green, green. This is colorless, colorless. So we are done with CJ. Now we now go to lilac. Lilac, we also pick one from the left and one from the right. So CGLLI. So now our next step is yellow, pink, yellow. So CGL, we are done with that. So yellow, pink, yellow, pale pink. So now yellow, pink, one from the left and one from the right. So yellow, pink, yellow, pink. We are done with yellow, pink. And now yellow, one from the left and one from the right. Yellow, yellow. And now what is our last color? We have the pale pink. Pale pink, one from the right, one from the left. So pale pink. So this is the easiest way you can record the colors of the lanthanide. Once you are in your exams hall, just make sure you have this color chart. CGL, yellow pink, yellow, pale pink, right? And you know the first one, which is colorless, you have to take two from the left, two from the right, one from the middle, right? Actually, if you count these elements, you can see that this gadolinium is the one in the middle, right? From the right side and to the left side, you see that this is actually what is in the middle. So first step, C, you take two from the left, two from the right. Then after that, G, which is green, one from the left, one from the right. Then after that, lilac, L, which is lilac, one from the left, one from the right. Yellow, pink, one from the left, one from the right. Yellow, one from the left, one from the right. Then pale pink, the remaining one, which is one from the right, one from the left. This is the easiest way to go about the colors of the lanthanide. When you're writing exams on the lanthanide series, you get a lot of MCQs on this. So just know this and you'll be good to go. Structure of elemental metals of lanthanide. So we know that the lanthanide series, those metals, they are made up of billions of atoms, right? Metals are made of billions of atoms. And those atoms do not just sit randomly. They arrange themselves in rectangular repeating patterns called crystal structures. So those are the structures that we are going to look at. Each of the elements, the lanthanide series had its particular structure. So first of all, I'm going to need you to take a close look at this chart here. So let me put this aside. So we have this shape indicating DHCP of OH, double hexagonal close packing. So element with this structure, so double hexagonal close packing atoms, right? And then HCP, hexagonal close packing. The atoms with elements with this shape shows hexagonal close packing. And CCP, cubic closed packing, right? And then BCC, body-centered cubic packing. So I'm going to show you an easy way to know this, right? An easy way to memorize this. Because depending on your professor, you'll be meeting a lot of questions under this, giving the element and be asked to state their shape. So now back to I drew them here with their various structures. So what you want to do now is that initially let's look at those that are unique. We have europium, right? Europium here showing BCC, body-centered cubic. This is europium, right? So first of all, figure out the exceptional one. Europium, BCC, BCC. So after that, let's look at the second one from the left and the second one from the right. Second one from the left here and the second one from the right here. Ytterbium and cerium. So they also show, a unique shape. So what is their shape? Well, this was CCP, CCP, right? CCP. So which one next? After this, we are left with, let's see here, from the remaining ones, from lanthanum, La to europium, you will see that they have the same structure, right? The same structure. We have the first, then third, fourth, fifth, sixth, they have the same structure. So they have the same structure right here. And what is that structure? It's just 4H, right? Or sometimes you won't see 4H, but you see um, hexagonal close packing, right? Or DHCP, which is hexagonal close packing. Let me write this for a word. DHCP, hexagonal close packing. Then the remaining one will be HCP. Sorry, this is double hexagonal close packing. And the remaining one will be hexagonal close packing, which is HCP. So what are the remaining elements here? You can see that after europium, we have GD, TB, DY, HO, and the last element. These ones have they have the same structure, which is HCP, hexagonal close packing. So I think for now, this is the easiest way to record the structure of the elemental metals. So you just have to know the memorize this BCC and then CCP. Then when you're done, you look at DHCP and the last one HCP. So you know that first one, you look at the exception which is europium. Europium shows BCC, right? Then after that, the second one from the left and the second one from the right are CCP, right? Which is second one from the right, second one from the left, CCP. And after that, those are the left hand side. The remaining ones are the left hand side after the production of elemental metals of the lanthanide series. So I've arranged the element in a certain manner that will be somehow easier for you to record them. So the elements on the lanthanide series, in the lanthanide series, there are ways of producing them elementally, right? So we are going to look at some equations that produce certain type of the elements in the lanthanide series. So for Le, Ce, Pr, Nd, Gd, this is the equation that you can use to produce them. So in your exams, your professor might decide to bring a couple of those elements and ask you to show how they are produced elementally. So you should know that as far as one of these elements are part of those, you should use this equation. So wherever you see you replace by the element, the given element. So you see we have the general equation to be 2mCl3 plus 3Ca and then 2m plus 3Cal2 into bracket temperature at high temperature greater than 1000 degrees Celsius, right? So imagine you be given that you should show how this element can be produced elementally, right? So you should have this equation in mind. You just have to know this equation before you be able to write to show how it is produced. So first of all, we have to take lanthanide. Wherever we see M, we put we have to take Le, lanthanum. So wherever we see M, we replace by L, right? So 2La, then Cl3 plus 3Ca giving us 2, there is M, then we replace it by La because we are showing how this is produced elementally. La is produced elementally, right? So 2La plus 3CaCl2. Then you should bring this depending on your professor. So 1000 degrees Celsius. So if it happens to be PR, this is what you should do. So you just have to keep this equation in mind. Wherever you see PR, you replace it by PR. So a sample question. Show by equation how the following elements, lanthanides, lanthanides are produced. So you see we have PR here. You can give in a couple of elements, a lot of elements on the lanthanide series and be asked to show how they are produced elementally. So you look at the element, depending on the element being given to you, we have a specific equation that you should go about it. So we have PR here. The PR, the only way to go about it here is with this equation. So you just have to know this equation. Wherever you see M, you replace it by PR, then you are good to go. So let's look at the rest. We are going to look at how each of the elements can be produced elementally. So far, the easier way to keep this in mind, the elements that can be produced using this equation elementally is LACE Pro NDGD. I think it sounds somehow I don't know how to say it, but I think it might help you in that way. So let's prove NDGD. Let's prove NDGD with this equation. Let's prove NDGD. So let's look at the other ones, how they can be produced. We have this here: HO, holmium, DY, erbium, TB, TM. So for these elements, this is how you can produce them elementally. So once again, you just have to keep this equation in mind, and wherever you see M, you know that you place it by the particular element. I mean, one of these elements, then you are good to go. So you can see that from the question, we have HO there, right? So here, if you have to show how this is produced elementally, so keep this equation in mind. So we are writing 2M. Wherever we see M, we replace it by O. I mean, sorry, HO, then F3 plus C, 3Ca, sorry, equal 2M here. We are producing HO, holmium, plus 3CaF2 into bracket. MCl is holmium, Cl3 is too volatile, right? Is too volatile. So how do you know the elements that can be produced? I mean, elementary with this equation. So I say HODA TBTM, HODA TBTM, HODA TBTM, HODA TBTM. Like the first one, let's prove NDGD. So let's look out the third one. I think we have 4 of the equations. So for this one, European Summit YB, European Summit YB. This is actually samarium, but this is the easier way that I used to record them. European Summit YB, they can be produced with this particular equation. You can see that from the question 2, we also have European. Your professor will bring a mixture of the elements to show how they are produced elementally. So just know the equations off head and the elements that can be produced using that, I mean, a particular equation. So here we have to show how European can be produced. So therefore, we therefore try to recall this equation. So we are looking at M2. Wherever you see M is the metal, right? European. So U 2O3 plus 2La giving us 2M. We are producing EU, right? Plus LeO3 into bracket M, which is EU, Cl3 is reduced to M, which is EU by Ca, right? By Ca. So just know the equation and you'll be good to go. The last one, which is lithium, PM. This is the only element in the Lanthanide series that you can use this equation to produce. So just simple as that. Just know the equation. You can see that from here we have it here, PM, how it is produced elementally. So just take note of this equation, you'll be good to go. Thank you very much for watching this video, and if you found this video helpful, kindly subscribe to my channel and like it for more content.